Right, wow. Weekly test six. Guys, this was not done particularly well. Um, uh, Especially considering that I just spent half an hour showing you exactly how to do all of this. Anyway, we're going to have to learn this. We've got to know how to do these sorts of questions because they're big marks and because it takes a while to draw all these things out. And once you've done it, it really does become very simple. But you do have to sit and learn how to do this. Sorry about this is a bit smaller. Can't focus the camera properly. Anyway, so in this question, we added LDA and then we added benzaldehyde. And I mean, everyone was clear that what benzaldehyde was. By third year chemistry, we'd expect you to be able to do that. The main thing is that when LDA forms the enolate of that one over there, there's only one place it can form the enolate, but the most important thing is that it forms, because of the T-butyl group, it forms the cis enolate. Now, actually, with all these questions, the question is explain, using suitable diagrams, why. All right, so explain why, explain why. You need to be able to, it's not just about drawing pictures, you need to put some notes here or there to actually give some sort of indication to me that I know what you're talking about. So, here you would say that the cis enolate is preferred. And depending on the number of marks that you will be associated, you might actually go on, well, it's preferred because the T-butyl is very bulky, etc., etc. So just always look at the number of marks to decide, how much detail you need to go in on a particular question. Then mechanistically, this is going to react with the benzaldehyde. And so if we stick the benzaldehyde over here, but we didn't have to do this for the answer, but anyway, that's the kind of thing that's going on. But the important thing is that the lithium counter ion is taking part in this as a six-member transition state, and so we work this out, work out with a Zimmermann-Traxler transition state. All right, and so we need to show that, and to do that, we set up a six-membered ring, all right, just the light form of that, and then we start putting everything in. I like to stick count the lithium there, or the boron, or whatever it is for a particular compound we're looking at. This is where the benzaldehyde is going, and we stick the phenyl group of benzaldehyde into an equatorial position. And then over here is the enolate, which is a cis enolate. So there's a double bond. T-butyl group must be in an axial position over there because it's sp2 carbon. It's flat, right? And so over here, the methyl group must be coming down, CH3, and going out this way would be the hydrogen atom. All right, so on the opposite side of the T-butyl group, right, it's on the same side as the oxygen. All right, so now the reaction occurs. There's a minus here, goes round like that, it goes to there, that's where we are forming a new bond, and this goes round to there, and we're going to form an ionic bond between that oxygen and that lithium. So we draw out finally what that looks like. So it's another little chair. Let's try and do it fairly neatly. All right, and this is why it's important to be able to do these. So lithium goes there. We've now got a double bond to this oxygen. We're going down to there. This bond is connected. This goes to the phenyl. This goes to the O. This up here goes to T-butyl. got an H going out there and a CH 3 going down there. All right. And so then we need to translate this to a flat structure. And there are a number of ways of doing it. Obviously, I'm going to stick the H over there as well. Obviously, the one way that you can do it is you can the one way that you can do it is to assign the chiral centers. Another way, some of you might be able to see this. If we look at this, here's the zigzag. All right, there's the zigzag pattern on the product, and here it is over there. So zig, zag, zig, zag. If you look at that, it's kind of like we're looking from the top down. We'll see that zigzag pattern. And when we do that, we see that the CH3 is pointing down and zigzag, zig, and the OH part is also pointing down. So when I drew this out, the product of this would look like, see, we've got phenyl, zig going to the OH, there it is down, zag, there's a CH3 going down, zig to ketone, zag to the, okay, maybe I got my zigs and zags mixed up, I don't know, but anyway, this transition state gives this product over here. So a lot of people are going with, it's R, and then you draw out the same thing over there and saying this one gives that, but it doesn't. Whoops. This one does not give that. This one actually gives the other enantiomer, but it's okay because the reaction is a little plus minus there, is racemic. All right. Okay, so hopefully you can see that. Anyway, some people thought that using a Falcon-On in this question was the correct, but there are no chiral centers next door to the aldehyde. There's no facial selectivity on that benzaldehyde. This question on the whole was done okay. So what we're doing is it's ethyl magnesium bromide. Apologize again for the resolution. The focus at least on this, but it's an ET minus effectively, and which is going to add to the aldehyde, and our product must look something, I guess, like an OH and an ET. So our product would look something like that, but we got to work out what this chiral center is going to be. And that's the tricky part. So in order to do that, we need to use the Falcon-On transition state. So we need to kind of stick our eye over there, and we're looking towards that. So as we look towards that, we see that above us is the aldehyde, and it's an aldehyde, so therefore we have an H over there, and then behind it, what we see is the phenyl group is going straight down, right? Because it's in the plane, OH is pointing up, phenyl is pointing straight down, so that's what's down there. And then we have the methyl group pointing out that side and the H over there. We then need to, so somewhere we need to say that use Falcon-On, and in order to set that up, we want to put the largest group at 90 degrees. All right, and so we switch that round. And so when we move that up, we put the hydrogen over there and the CH3 over there. This one over here is the wrong one, because this attack over here of the nucleophile is sterically hindered. This attack of the nucleophile over there is sterically hindered, so we have to swing it round again. And so we draw it out. The phenyl is over there, and CH3 is there, and the H is over there. And so now this is preferred because no steric blockage. All right, so looking at our original structure, the way we looked at the thing, we see the nucleophile wants to come in from this side, which is below. So it's coming in from underneath. So the way we draw out this product, because if we try to do it here, we're going to get wrong. The way we draw out the product is we draw everything out exactly as we would have, as we've got it, going to there. There's an H that's in the plane, and this is where a lot of people made mistakes. And yeah, and the O is going to be pushed up because the nucleophile comes in from below. And you can leave the answer like that. It's perfectly okay. If you spin it round, I think you'll find that that's the correct answer there. The tragedy with this sort of question is that for a lot of you, you drew out this incorrectly. So you had the enantiomer of this one, so already on the wrong track. And then when you worked out the answer, you made another mistake and inverted it again. So you ended up getting the right answer. It's one of the few cases in life where two wrongs apparently make a right. But that's not true for the rest of life, please. All right. Okay. Hopefully that helps a little bit. Cheers.